Tonight, we are going to travel to the very edge of our solar system. Not to Neptune, not to Pluto, not even to the Kuiper Belt, but far, far beyond all of those. We are going to the place where the sun's gravity barely holds on, a place so remote, so vast, and so profoundly empty that most people have never even heard of it. A place that exists at the boundary between our solar system and the open ocean of interstellar space. It is called the Oort Cloud. And by the end of tonight, you are going to understand why this single structure is the most distant and most mysterious thing hiding at the edge of everything we know, and why, when you truly grasp its scale, you will never see the solar system the same way again. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Every map has an edge, and for most of human history, the edge of the solar system has been wherever our knowledge ran out. First it was Saturn, the furthest planet visible to the naked eye, then Uranus, then Neptune, then Pluto. Each time we found something new, the edge moved. But there is one boundary that has barely entered public consciousness at all, one that sits so far out, so dark, and so cold that we have never seen it directly. The Oort Cloud is not just far away. It is so far away that the concept of far starts to break down. To understand just how far, you have to start close and work your way out. Earth orbits the Sun at an average distance of about 93 million miles. That number is the foundation of almost all astronomical measurement. Astronomers call it 1 astronomical unit, or 1 AU. Light crosses it in about 8 minutes. Now, let's use that unit to move outward until the numbers stop making sense. Mars sits at about 1.5 AU. Jupiter, the first of the gas giants, lies at roughly 5 AU. By the time you reach Saturn, with its rings, its moons, its golden haze, you are 9.5 AU from the Sun. Uranus is 19 AU out. Neptune, the most distant of the 8 planets, orbits at about 30 AU. These are the planets, the ones astronomers tracked for centuries before the invention of the telescope, the ones whose gravity shapes the inner solar system, shepherds the asteroid belt, and governs the orbits of countless smaller bodies. At 30 AU, you might reasonably think you have reached the edge of the solar system. You have not. Not even close. When the Voyager probes passed Neptune in the late 1980s, mission controllers celebrated what they framed as the completion of the planetary tour. And it was a monumental achievement. Both probes had visited Jupiter, Saturn, and their moons. And Voyager 2 had continued to Uranus and Neptune in a grand tour made possible by a rare alignment of the outer planets that only occurs once every 175 years or so. But passing Neptune was not reaching the edge of anything. It was reaching the end of the planetary section of a much, much longer journey, like clearing the front door of a continent-spanning wilderness. The territory beyond Neptune dwarfs everything that came before it, so completely that framing Neptune as any kind of boundary is almost comically misleading. Beyond Neptune begins a region called the Kuiper Belt. It is a broad disk of frozen objects orbiting the Sun in roughly the same plane as the planets, extending from about 30 AU out to around 50 AU. This is where Pluto lives, reclassified in 2006 as a dwarf planet, but still one of the most famous objects in the outer solar system. Pluto orbits between roughly 30 and 49 AU from the Sun, swinging in and out on an elliptical path. The Kuiper Belt is filled with icy bodies, dwarf planets, ancient remnants of the solar system's formation, worlds that never quite assembled into something larger. Eris, Makemake, Haumea, all residents of this outer disk. The farthest confirmed Kuiper Belt, objects sit at around 50 AU. At 50 AU, light from the Sun has been traveling for almost 7 hours to reach you. The Sun still exists, still dominates the sky, but it has shrunk to something that looks more like a very bright star than the blazing disk we know from Earth. From Pluto, the Sun is about 1,000 times fainter than it appears from here, still bright enough to cast shadows, in principle, but diminished, cold, remote. The Kuiper Belt itself is an extraordinary region that we have only begun to understand. The New Horizons spacecraft, launched in 2006, flew past Pluto in 2015 after a journey of 9.5 years. When it finally arrived and the images came back, a heart-shaped nitrogen glacier, mountains of water ice, a hazy, layered atmosphere, they shocked nearly everyone. Pluto was not the dead, featureless rock that many had expected. It was a dynamic, complex world with weather and geology. And it orbited in what was suddenly, evidently, a rich and varied outer solar system that we had barely begun to map. New Horizons continued outward after Pluto, and in 2019 flew past a small Kuiper Belt object called Arrokoth, a contact binary, 2 lobes of reddish material stuck gently together, shaped like a flattened snowman. It was the most distant object any spacecraft had ever visited, sitting at roughly 44 AU, a remarkable achievement, and still less than 0.1% of the way to the outer Oort Cloud. 50 AU still sounds large, and it is large. But it is nothing at all compared to what lies beyond it. Past the Kuiper Belt, there is a zone that astronomers sometimes call the scattered disk. This is where objects have been gravitationally scattered by Neptune's gravity into elongated, highly inclined orbits that take them far beyond the classical Kuiper Belt. Objects in the scattered disk have perihelia, their closest approach to the Sun near Neptune's orbit, but their aphelia extend outward to hundreds of AU. They are objects that Neptune grabbed and flung, repeatedly perturbed, set on wild arcing paths that carry them in and out of the inner solar system's gravitational neighborhood over millions of years. One of the most remarkable objects in this region is Sedna. Sedna was discovered in 2003 and immediately confused astronomers. Its orbit is extraordinarily elongated. At its closest approach to the Sun, it sits at about 76 AU. At its farthest, it travels out to roughly 937 AU. 937 AU. Think about what that means. Neptune orbits at 30 AU. Sedna, at its farthest, orbits at more than 30 times Neptune's distance. And yet Sedna is not in the Oort Cloud. It might be what some astronomers call an inner Oort Cloud object, or it might represent a transitional population sitting between the Kuiper Belt and the true Oort Cloud. Either way, its existence was a hint, a glimpse of something lurking far beyond anything the solar system's planets could have placed there by ordinary gravitational sculpting, because Neptune's gravitational reach extends to roughly 30 AU. Sedna's perihelion is at 76 AU. Neptune could not have put Sedna there. Something else did. Something operating at distances and timescales that the known solar system could not explain. Sedna pointed outward, and what it pointed toward was something that had been theorized for decades, but never directly seen. The story of the Oort Cloud as a scientific concept begins in the 1940s and 50s. Astronomers had long noticed something peculiar about a certain class of comets. These were not the short-period comets, the ones like Halley's Comet, which return every few decades on predictable schedules, falling in from just beyond Neptune and swinging around the Sun in orbits that are reasonably well understood. Halley's Comet, for example, has an orbital period of about 75 to 76 years and originates in the Kuiper belt, or the scattered disk. Its orbit is well known, its returns predictable. Astronomers have traced its apparitions back thousands of years. But there was another class of comets, entirely long-period comets, that arrived from seemingly random directions in the sky, not confined to the ecliptic plane where the planets orbit, but coming in from above, from below, from all angles. Comets with orbital periods not of decades, but of millions of years. Comets that, when their orbits were calculated backward, appeared to come from distances of tens of thousands of AU. Nobody had a satisfying explanation for them. In 1950, a Dutch astronomer named Jan Hendrik Oort published a landmark paper. Oort was already one of the most distinguished astronomers of his era. He had made foundational contributions to our understanding of the structure and rotation of the Milky Way. He had helped establish that the galaxy rotates differentially, that the inner parts rotate faster than the outer parts, and he had used observations of stellar motions to estimate the position of the galactic center long before it could be directly observed. When Oort turned his attention to comets, he brought the same rigorous analytical approach. He analyzed the orbital data of a sample of long-period comets and noticed something striking. The aphelia, the farthest points of their orbits, clustered at very large distances, somewhere between 20,000 and 100,000 AU. There was a spike in the distribution. Too many comets had their aphelion in that range for it to be a coincidence. There seemed to be a shell, a reservoir of cometary material, surrounding the entire solar system at enormous distance. Oort proposed that this reservoir was a remnant of the original cloud of material that formed the solar system. Leftover icy bodies, nudged outward by gravitational interactions with the giant planets during the solar system's turbulent early history, now sitting in a vast spherical halo, far beyond anything the planets could reach directly. This reservoir, he argued, was occasionally disturbed by the gravity of passing stars, by the gravitational tidal forces of the Milky Way itself, by encounters with molecular clouds drifting through the galaxy. Those disturbances would occasionally dislodge objects from the reservoir, sending them tumbling inward on long, arcing paths toward the Sun. We call those objects long-period comets, and the reservoir is what we now call the Oort Cloud. Oort did not name it after himself. Scientists rarely do. But his peers and successors recognized the profound importance of his insight, and the name stuck. The Oort Cloud has never been directly observed. This is a fact worth sitting with for a moment. We have never pointed a telescope at the Oort Cloud and seen it. No spacecraft has reached it. No direct detection of any individual Oort Cloud object at its actual location has ever been confirmed, though some candidates have been proposed. Everything we know about it is inferred from the orbital properties of the comets that arrive here, from theoretical models of how the solar system formed, from numerical simulations of how billions of small icy bodies would behave under the combined gravitational influences of the giant planets, nearby stars, and the galactic tide. It is one of the strangest things in planetary science, an enormous structure, arguably the largest structure associated with our solar system, that no one has ever seen. Its existence is about as well established as a scientific idea can be without direct confirmation. The orbital mechanics work out too consistently. The comets arrive from exactly the right distances in exactly the right pattern for the Oort cloud not to exist. But its invisibility is also a direct consequence of its nature. The objects in the Oort cloud are small, dark, and impossibly distant. Even if you aimed the most powerful telescope ever built at the right patch of sky, you would not see anything unless an object happened to catch sunlight at just the right angle, and at those distances, there is almost no sunlight to catch. The sun's luminosity falls off with the square of distance. At 1 AU, the sun delivers about 1,360 watts of energy per square meter. At 100,000 AU, the outer edge of the Oort cloud, that number has been reduced by a factor of 10 billion. The sunlight out there is 10 billion times fainter than what reaches Earth. Objects that reflect even a small percentage of that faint light would be effectively invisible to any telescope currently in existence. The Oort cloud hides not because it is small, but because it is dark and distant and spread across such an enormous volume of space. So how far out does the Oort cloud actually extend? The inner edge is uncertain, but many models place it starting somewhere around 2000 AU, possibly extending from the outer edge of the scattered disk. The outer edge is estimated at somewhere between 50,000 and 200,000 AU. The most commonly cited figures sit around 100,000 AU for the outer boundary. 100,000 AU. Let's convert that to something more tangible. 1 AU is about 93 million miles. 100,000 AU is approximately 9.25 trillion miles. Light travels at about 186,000 miles per second. At 100,000 AU, the light from the Sun takes about 1.5 years to arrive. The outer Oort cloud sits roughly 1.5 light-years from the Sun. The nearest star to our Sun is Proxima Centauri, at a distance of about 4.2 light-years. The outer Oort cloud extends about 1/3 of the way to the nearest star. Our solar system's gravitational reach, the Sun's claim on matter, extends more than 1/3 of the distance to the nearest stellar neighbor. The solar system does not end at Neptune. It does not end at the Kuiper belt. It does not end at Pluto, or Sedna, or any object we have yet named. It ends in a vast, dark halo of ice and rock that nobody has ever seen, sitting at the edge of interstellar space. The structure of the Oort cloud is generally divided into two broad components. The inner Oort cloud, sometimes called the Hills cloud after the astronomer Jack Hills, who proposed its existence in the 1980s, sits closer in roughly 2,000 to 20,000 AU. Jack Hills argued that because the outer Oort cloud is so easily disrupted by passing stars and the galactic tide, it must constantly be replenished from somewhere closer in. The inner cloud, more tightly bound and less susceptible to perturbation, would serve as a reservoir that slowly feeds the outer cloud. The inner Oort cloud is thought to be more disk-like or toroidal in shape, a thickened ring rather than a complete sphere, still retaining some memory of the flat disk geometry from which the solar system formed. The outer Oort cloud, extending from about 20,000 to 100,000 AU or beyond, is believed to be more or less spherical, a shell surrounding the solar system in all directions. This spherical geometry is itself a clue to the Oort cloud's history. The planets all orbit in roughly the same plane because they formed from a flat disk of material rotating around the young Sun. The Kuiper belt objects largely respect this same plane. But the outer Oort cloud shows no such preference. Long-period comets arrive from random directions in the sky, from all inclinations, not clustered near the ecliptic. That randomness tells astronomers that whatever population of objects sits out there, their orbits have been scrambled. The originally disk-like swarm of icy bodies that were scattered outward from the inner solar system during the giant planet migration had their orbits randomized over billions of years by the galaxy, gravitational tides of the Milky Way, and by close encounters with passing stars. Those gravitational influences, operating over billions of years, slowly tilted and rotated the orbits until they pointed in all directions. The Oort cloud became a sphere. An enormous, diffuse, dark sphere of frozen material wrapped around everything we have ever known or discovered. What is actually in the Oort cloud? The honest answer is that we do not know precisely because we have never seen it directly. But based on the comets that reach us, we can make reasonable inferences. The objects are primarily composed of water, ice, carbon monoxide, carbon dioxide, methane, and ammonia, the volatile, low-temperature ices that condense in the outer solar system. They are mixed with dust, silicate grains, and organic compounds, complex carbon-bearing molecules that form readily in the cold chemistry of the outer solar system and in the interstellar medium from which the solar system originally formed. When a long-period comet is dislodged from the Oort cloud and falls inward, the heat of the sun causes these ices to sublimate, to go directly from solid to gas, creating the spectacular tails that make comets visible. The coma, the diffuse cloud of gas and dust surrounding the nucleus, can grow to sizes larger than some planets. Comet tails can extend for tens of millions of miles. Yet, all of this comes from a nucleus, the actual frozen body that is typically somewhere between 1 and 10 miles across. The famous comet Hale-Bopp, which brightened the sky in the late 1990s and was visible to the naked eye for months, had a nucleus estimated at between 25 and 40 miles across, unusually large, which is part of why it was so bright, even though it never came especially close to Earth. Its perihelion was actually just inside Earth's orbit, at roughly 0.91 AU from the Sun, closer to the Sun than Earth. But because of its orbital geometry, it passed no closer to Earth than about 1.3 AU. And still, it blazed. How many objects are in the Oort cloud? Current estimates suggest somewhere between 100 billion and several trillion individual objects, large enough to be called comets, that is, bodies larger than roughly 1 mile in diameter. The total mass of the Oort cloud is extremely uncertain. Estimates range from roughly a few Earth masses up to perhaps a few dozen Earth masses, though some models allow for substantially more. The large uncertainty reflects how little we actually know about this region directly. We are doing astronomy by inference, by the trails left behind when the occasional object escapes the reservoir and falls inward to announce itself. It is like trying to estimate how many fish are in the ocean by counting only the ones that wash ashore. The question of where the Oort cloud objects came from is one of the central stories of solar system formation. The original picture, which held sway for much of the 20th century, was reasonably straightforward. The objects in the Oort cloud formed in the region of the giant planets, roughly between Jupiter and Neptune, and were scattered outward during the turbulent early history of the solar system. When Jupiter and Saturn formed and reached their current masses, they hurled vast numbers of small, icy bodies outward with their gravity. Some of those bodies were ejected from the solar system, entirely lost to interstellar space forever. Others were flung far out, but not quite far enough to escape, ending up in highly elongated orbits with aphelia at thousands or tens of thousands of AU. Gradually, over hundreds of millions of years, the galactic tide and passing stars rounded out the innermost parts of those orbits, lifting their perihelia, their closest approach, distances away from the giant planets. Those bodies became the Oort Cloud. This picture is still broadly accepted. But modern simulations that model the early solar system with far more detail than was possible in Oort's time have deepened and complicated it. One major revision comes from the understanding that the Sun almost certainly formed in a stellar cluster, a dense group of perhaps hundreds or thousands of young stars, all forming together from the brightening, same giant molecular cloud. This was not an unusual birth. The vast majority of stars in the galaxy are thought to form in clusters, at least initially. Most clusters disperse over tens of millions of years as the stars drift apart, dispersed by gravitational interactions and the pressure of the stellar winds of the most massive members. But during those early tens of millions of years, the cluster is dense. Stars are close together. Passages between young solar systems are common. That early cluster environment would have had profound consequences for the Oort Cloud. Neighboring stars, much closer to the Sun than any star is today, would have gravitationally influenced the orbits of objects scattered outward by the giant planets, helping to shepherd them into the cloud more efficiently and shaping the cloud's early structure. Objects that might have escaped into interstellar space under isolated conditions could instead have been captured and retained by the combined gravitational influence of the cluster. The early Oort Cloud may have been far more massive than it is today, its initial population partly shaped by the dense stellar environment of the Sun's birth cluster. As the cluster dispersed and the Sun found itself in the relative isolation of the galaxy's disk, the outer Oort Cloud became more susceptible to disruption. Its outer reaches began to be stripped away by passing stars. The population declined. What we have today may be a significantly depleted version of the original cloud. Some models even suggest that a significant fraction of objects in the Oort Cloud may not have formed in our solar system at all, but were captured from the protoplanetary disks of neighboring stars. When the cluster was young and stellar passages were frequent, when two young star systems pass within a few thousand AU of each other, which is common in dense clusters, material can be exchanged. Objects in the outer disk of one system can be gravitationally captured by the other. The Oort Cloud might be, in part, a stolen archive from other solar systems. Objects that formed around other stars, circling alien suns for a brief period before the gravitational chaos of a young star cluster tore them loose and deposited them into orbit around our own Sun. This idea is taken seriously by planetary scientists, though the exact fraction of captured material is deeply uncertain. The Oort Cloud's formation history is one of the least understood chapters in the story of our solar system. Once objects are in the Oort Cloud, they do not simply sit there undisturbed forever. The Oort Cloud is not a static archive. It is a dynamic reservoir, constantly being perturbed, constantly losing objects to either the inner solar system or to interstellar space. The main forces driving this dynamism are the gravitational tides of the Milky Way and the gravitational influence of passing stars. The galactic tide is a subtle but powerful effect. The Milky Way is not homogeneous. There is more mass concentrated toward the galactic center and along the galactic plane than in other directions. As the solar system orbits the galactic center, a journey that takes about 225 to 250 million years to complete the net gravitational pull on the Sun and its surroundings, varies in a complex way. This differential gravitational pull, the galactic tidal force, acts on objects in the Oort cloud. For objects in the outer Oort cloud, the galactic tide is actually the dominant perturbing force. It is stronger than the gravitational influence of passing stars on average, though passing stars can be far more powerful in individual close encounters. The galactic tide works primarily on the perpendicular component of orbital motion, the motion out of the galactic plane. It acts slowly, continuously torquing the orbits of Oort cloud objects in a way that gradually changes their perihelion distances over millions of years. When the perihelion of an Oort cloud object drops to within the range of Neptune's influence, roughly 30 AU, Neptune's gravity can then modify the orbit further, eventually sending the object diving into the inner solar system. This is the primary mechanism that delivers new long-period comets to the inner solar system on an ongoing basis. The galactic tide does not produce a constant, steady stream. It produces a rhythmic variation. As the solar system bobs up and down through the galactic plane during its orbit around the galactic center, the tidal forces change in a periodic way. Some researchers have proposed that this periodic variation in comet delivery might explain certain apparent cycles in Earth's impact and extinction record, though this idea remains controversial and not universally accepted. The second major perturbing force is passing stars. Stars are not fixed. They move through the galaxy on their own paths, and every few million years, on average, a star passes close enough to the solar system to noticeably perturb the outer Oort cloud. Most passages are at distances of a light year or more and have only gentle effects. But occasionally, a star passes closer within half a light year, or even closer still. Such a close passage can send a shower of comets inward, dramatically increasing the flux of long-period comets arriving in the inner solar system for a period lasting millions of years. The perturbing star effectively reaches into the outer Oort cloud, shakes it, and dislodges swarms of icy bodies. We know this happens because we can calculate the past trajectories of nearby stars and identify which ones have passed close to the solar system in the recent past. A red dwarf star named Schultz's star, along with its companion brown dwarf, is believed to have passed within roughly 0.8 light-years of the Sun, roughly 70,000 years ago. That is well within the outer Oort cloud. A passage like that would have perturbed the orbits of countless objects in that region, potentially dislodging a population of comets that will eventually, millions of years from now, fall inward and announce themselves as long-period comets. The comets we see today, arriving from the depths of the Oort cloud, are the long-delayed consequences of stellar encounters that happened millions of years in the past. And some comets that were disturbed by encounters even further back, hundreds of millions of years ago, have still not arrived. They are still falling, still on their way. The sky above us is the visible endpoint of countless journeys that began before complex life existed on Earth. A long-period comet falling inward from the Oort cloud carries no record of the time it spent in transit. It does not know it has been traveling for 5 million years. But we can calculate it. We can work backward from the orbit, trace the trajectory, and determine where the object came from and how long the journey took. And when you do that calculation, the timescales involved are genuinely staggering. The discovery, in 2017, of a small object moving through the inner solar system on a hyperbolic trajectory changed the conversation about the solar system's relationship to interstellar space in a dramatic way. The object was named Oumuamua, a Hawaiian word meaning something like first distant messenger, and it was moving too fast to be bound to the solar system. It had come from interstellar space. Oumuamua was the first confirmed interstellar object ever observed passing through our solar system. It moved in from the direction of the constellation Lyra, swung around the Sun, and accelerated outward again, showing a peculiar non-gravitational acceleration that was difficult to explain through conventional cometary outgassing, since no coma or tail was ever detected. Its shape appeared to be extremely elongated, possibly cigar-shaped or flat and disc-like. Though with only a handful of observations, its true morphology remains uncertain. The scientific community debated intensely about whether Oumuamua was a comet, an asteroid, a fragment of a disrupted planet from another system, or something more exotic. It left the solar system before answers could be found. In 2019, a second interstellar object was discovered, Comet Borisov. Unlike Oumuamua, Borisov was unambiguously cometary. It displayed a clear coma and tail as it was heated by the sun. It looked like a normal comet in every respect, except that it was clearly on a hyperbolic trajectory, arriving from outside the solar system. What does this have to do with the Oort Cloud? If interstellar objects pass through our solar system, it means other solar systems eject material too. When another star's equivalent of a giant planet migration scatters small icy bodies outward, some of them escape into interstellar space and roam the galaxy. Our Oort Cloud formed partly by losing objects to interstellar space, the same kind of objects that are now passing other systems as interstellar visitors. The interstellar medium is filled, at low density, with the ejecta of billions of planetary systems. The galaxy is quietly exchanging material between solar systems, not frequently enough to matter much in terms of overall planetary composition, but enough to be detectable. The Oort Cloud is not just our solar system's attic. It is part of a much larger galactic ecosystem of material, a cosmic recycling process operating on timescales of billions of years, in which the raw ingredients of solar systems scatter, drift, and occasionally end up somewhere new. There is a boundary that sits at the very outer edge of the Sun's gravitational domain. It has a formal name, the Hill Sphere. The Hill Sphere of the Sun is the region within which the Sun's gravity dominates over the gravitational influence of the Milky Way galaxy itself, or more precisely, the tidal force from the galactic mass distribution. For the Sun, the Hill Sphere extends to roughly 1 to 2 light-years, consistent with the outer boundary of the Oort Cloud. Beyond the Hill Sphere, objects can no longer be considered gravitationally bound to the solar system in any meaningful long-term sense. The galactic tidal force will eventually strip them away. The outer Oort Cloud sits right at this boundary. The objects out there are barely bound. Some of them have orbital energies so close to zero, the threshold between bound and unbound, that the gravitational nudge from a passing star, or even a slightly different position in the galactic tidal cycle, could liberate them. They hover at the edge. And this is what makes the Oort Cloud the true outer boundary of the solar system. Not a sharp line, not a wall, but a gradient, a region where the Sun's ownership of matter gradually gives way to the indifferent embrace of the galaxy. The solar system doesn't end with a boundary you can point to. It dissolves. The concept of the solar system is itself slightly fuzzy at these extremes. At some distance, the Sun's gravity becomes comparable to the random gravitational nudges of nearby stars. At some distance, an object's orbit is perturbed so frequently by external influences that saying it belongs to the solar system becomes a matter of convention more than physics. The Oort Cloud occupies exactly that ambiguous zone. It is the solar system's borderland, the region where our star's influence ends and the galaxy's begins. Everything in the Oort Cloud formed roughly 4.5 billion years ago, along with the rest of the solar system. The Sun condensed from a collapsing molecular cloud. The inner planets assembled from dust and rock within the first 100 million years. The outer solar system built its gas giants in the first few million years, perhaps even faster. And as those giants grew, they scattered the remaining debris of their formation. Billions upon billions of small icy bodies in all directions. Some fell into the Sun. Some were ejected entirely and now drift in interstellar space. Many ended up in the Kuiper Belt and the scattered disk. And many, perhaps the original population, numbered in the hundreds of billions, were flung to vast distances and over billions of years settled into what we now call the Oort Cloud. The objects sitting in the Oort Cloud have not changed significantly since then. They are 4.5 billion years old. They have been sitting in cold storage since the solar system was young, never warmed by the sun, never exposed to the chemistry-altering effects of radiation that heat them when they become comets, never involved in any of the grand events that shaped the inner solar system. No volcanism, no erosion, no impacts of significance, just cold, just stillness, just the slow, vast orbit carrying them around the sun at a pace so glacial that the entire span of human civilization represents only a vanishingly small arc of their total journey. They are time capsules. When a long-period comet falls inward from the Oort Cloud for what is often the very first time, what arrives in the inner solar system is essentially unaltered material from the original planetary nebula. The molecules released water, carbon monoxide, carbon dioxide, methane. Complex organic compounds tell us about the composition of the protoplanetary disk from which everything in the solar system formed. Studying Oort Cloud comets is, in a very real sense, studying the beginning. The chemistry of these objects has not been processed by heat or pressure in 4.5 billion years. The carbon compounds in their interiors may be among the most ancient, unaltered, organic molecules in the solar system. When astronomers analyze the spectra of long-period comets, they are reading a chemical record from an era so remote that nothing alive today has any connection to it other than the atoms shared between all matter. There is a particular subset of comets that has a special significance in this story. When a comet from the Oort Cloud falls inward for the very first time, it is called a dynamically new comet. It has never been heated by the sun before. Its surface is pristine, covered in a thick layer of the most volatile ices, the substances that sublimate at the lowest temperatures. When these dynamically new comets approach the sun, they often outgas dramatically well beyond the orbit of Jupiter, brightening much earlier than more evolved comets that have already been stripped of their outer volatile layers by previous passages. A first-time visitor from the Oort Cloud will begin developing a coma even when it is still more than 5 AU from the sun. It is releasing its outermost volatiles carbon monoxide, carbon dioxide substances that boil off at temperatures far lower than water ice. This early brightening is a signature. It identifies the comet as a newcomer, an object making its first approach. And that distinction matters scientifically, because a dynamically new comet's chemistry has never been processed by the Sun's heat. It carries the original molecular inventory from the protoplanetary disk. Comets that have made many previous passages have had their most volatile compounds already cooked away. They are depleted, evolved, more like the processed remnants of their original composition. The dynamically new ones are the pristine originals. What makes this observationally important is the concept of the Oort Cloud spike. When astronomers plot the distribution of orbital energies of long-period comets, they find a notable excess of comets with very long periods of millions of years, corresponding to aphelia in the outer Oort Cloud. This spike in the distribution represents freshly dislodged objects falling in for the first time. The spike tells you where the reservoir sits. It is essentially a direct observational signature of the outer Oort Cloud's existence, even though no individual Oort Cloud object has been resolved at its actual location. The cloud announces itself through the comets it sends. Oort himself used exactly this logic in his original 1950 paper. He noticed the spike in the orbital energy distribution, recognized what it implied, and proposed the reservoir to explain it. It was one of the great inferences in planetary science, using the messengers to deduce the existence of a place no telescope could reach. It is the kind of reasoning that defines science at its most elegant. You cannot see the forest from where you stand, but you can see the seeds it produces. And from those seeds, you reconstruct the forest. The fate of the Oort Cloud over cosmic time is a sobering subject. It is being depleted, slowly but continuously. Some fraction of the objects disturbed by the galactic tide and passing stars fall inward and are either ejected by Jupiter's gravity, driven into the Sun, or lost to interstellar space after a planetary encounter. Some are simply stripped away by passing stars. Over billions of years, the Oort Cloud is losing material. It has already lost a great deal since the early solar system, when the initial population of scattered bodies was far larger. The cometary flux we see today, the rate at which long-period comets arrive in the inner solar system, is thought to be much lower than it was during the first billion years of the solar system's existence. The reservoir has been drawn down, and the drawing down continues. In the far future, as the solar system continues orbiting the galaxy and passing through regions of varying stellar density, encountering molecular clouds and passing through the denser inner regions of the galaxy on its long orbital journey, the depletion will continue. There is also the question of what happens when the solar system passes through a particularly dense region of the interstellar medium or through a molecular cloud. Such passages can dramatically increase the rate of stellar encounters and the strength of external gravitational perturbations. Some researchers have proposed that the solar system passes through the denser midplane of the galaxy roughly every 30 million years, as it bobs vertically in its galactic orbit. If that passage correlates with enhanced comet delivery, it could explain certain periodicities observed in the terrestrial impact record. The evidence for this periodicity is debated, but the physics of enhanced perturbation during galactic plane crossings is well established. The Sun is also aging. In roughly 5 billion years, the Sun will exhaust the hydrogen in its core and begin expanding into a red giant. It will swell to perhaps 100 times its current diameter before eventually shedding its outer layers and leaving behind a small, cooling remnant called a white dwarf. When the Sun becomes a white dwarf, its total mass will be significantly less than it is today, roughly half. When the mass of the central body decreases, the gravitational binding energy of everything orbiting it decreases proportionally. The Oort cloud, already barely bound, will be significantly disrupted. Many of the objects hovering at its outer edge will be stripped away entirely as the Sun loses mass. Some will fall inward and be briefly heated before the dying Sun can no longer sustain their sublimation. Others will drift away into the galaxy, becoming interstellar wanderers. The Oort cloud, in its current form, will not survive the death of the Sun. It will disperse. Its objects will scatter, some consumed, some ejected, most simply drifting away into interstellar space to join the vast, cold population of rogue icy bodies roaming the galaxy between the stars. This is the ending that awaits the most remote territory of our solar system. Not a dramatic explosion, not a collision, not a sudden ending, just a slow release. A quiet dissolution as the Sun loses its hold. One of the most profound implications of the Oort cloud scale is what it means for our ability to explore it. Voyager 1 is currently our most distant spacecraft. It was launched in 1977 and has been traveling outward ever since, crossing the termination shock of the heliosphere and crossing the heliopause, the boundary between the solar wind and the interstellar medium, in 2012. Voyager 1 is now in interstellar space. As of 2026, it is approximately 167 AU from the Sun. It is the farthest human-made object that has ever existed. 167 AU. That number might sound large, but the inner edge of the Oort cloud begins at roughly 2000 AU, and the outer edge is at 100,000 AU. Voyager 1, our fastest ever outbound spacecraft, after nearly 50 years of travel, has covered about 167 AU. At its current speed of roughly 38,000 miles per hour, it would take approximately 300 years to reach the inner edge of the Oort cloud. To reach the outer edge would require tens of thousands of years. These numbers are not a planning problem. They are not a challenge that a better rocket would solve, at least not with any propulsion concept grounded in current physics. They represent a fundamental truth about the Oort cloud. With any propulsion technology that currently exists or is plausibly on the horizon without radical new physics, the Oort cloud cannot be explored directly in human timescales. Not in the timescales of missions or agencies. Not in the timescales of nations or civilizations. Not in any timescale that human beings have ever managed to plan around. Various exotic propulsion concepts have been proposed over the years: solar sails, laser propulsion systems, nuclear pulse drives. Some of these could potentially accelerate a small probe to a fraction of the speed of light. A probe traveling at 1% of the speed of light could reach the inner Oort cloud in a few centuries, the outer edge in perhaps 15,000 years. Still an incomprehensible timescale for any human institution. And even the most optimistic propulsion concepts cannot get past the communication problem. A probe at 50,000 AU would be so distant that signals sent at light speed would take nearly 8 months to arrive. Any discovery it made would reach us 8 months after the fact, and any response we sent would take another 8 months. Science at these distances requires fully autonomous probes capable of making their own decisions without waiting for instructions from Earth. Technology that does not yet exist in any useful form. This is what makes the Oort cloud unique among the major structures of the solar system. Everything else, every planet, every moon, every major asteroid, every Kuiper Belt object of note is at least theoretically reachable. with mission concepts that exist or could plausibly be built. The Oort Cloud is not. It is, in the most literal sense, unreachable by human technology for the foreseeable future. We know it is there. We infer its properties with reasonable confidence. We watch its messengers arrive in the inner solar system and analyze them carefully. But the cloud itself remains inaccessible, observed only through the comets it occasionally releases. It is a place defined by inference rather than exploration. There is something worth dwelling on here. The solar system, as most of us picture it, ends at Neptune. When space agencies produce maps of our cosmic neighborhood, they typically show the 8 planets and stop there. When school children are taught about the solar system, it ends at Neptune. Even when Pluto is included, and it often is. As a beloved footnote, the implication is that the solar system is a compact, reasonably well-defined structure with an outer boundary somewhere in that general region. But the reality is that the solar system extends to 100,000 AU. It extends to 1.5 light years. The region we have explored, the region where any spacecraft has ever traveled, the region we have mapped and measured and visited, is a tiny fraction of the solar system's true extent. The planets, all 8 of them, from Mercury at the inner edge to Neptune at 30 AU, occupy roughly 0.03% of the distance from the Sun to the outer Oort Cloud. Everything we have ever explored, everything we have ever photographed, every planet, every moon, every asteroid visited by a spacecraft, all of it occupies less than 1 part in 3,000 of the solar system's total radial extent. The other, 99.97%, is the Oort Cloud. Dark, cold, silent, filled with billions of objects that have not moved significantly since the solar system was born. This is the true scale of the solar system, not the tidy diagram in the textbook, not the 8 planets arranged in a neat row. A vast, dark envelope of frozen material stretching halfway to the nearest star, surrounding everything we know in a shell so enormous it makes the entire planetary system look like a grain of sand at the center of an empty stadium. And because of the way volume scales with radius, the disproportion becomes even more striking when you account for 3 dimensions. The volume of a sphere is proportional to the cube of its radius. Neptune orbits at 30 AU. The outer Oort Cloud extends to 100,000 AU. The ratio of those radii is roughly 3,300. The ratio of the volumes, the volume enclosed by Neptune's orbit versus the volume enclosed by the outer Oort Cloud, is that number cubed. Roughly 36 billion. Everything we have ever explored, everything we have ever seen, every planet and moon and ring and spacecraft and comet we have watched streak across our sky. All of it fits into a volume that is 36 billion times smaller than the full extent of the solar system. The solar system is almost entirely the Oort Cloud, and the Oort Cloud is almost entirely empty. An extraordinary region of almost perfect nothing, scattered through with billions of frozen messengers from the beginning of time, held loosely by a star's fading gravitational grip, slowly dissolving into the galaxy over the course of billions of years. This is where the solar system really ends. Not at Neptune, not at Pluto, not at any named world or any explored boundary. Here, in the dark, where the sun is just a star. In recent years, the search for additional bodies that might tell us more about the inner edge of the Oort Cloud has accelerated. The discovery of Sedna in 2003 was followed years later by the discovery of another similar object, given the provisional designation 2012, VP-113. VP-113 has a perihelion of roughly 80 AU, even further out than Sedna's closest approach. Both Sedna and VP-113 orbit in a region of space between roughly 70 and 2000 AU. That should, according to standard models, be essentially empty. The known giant planet's gravitational reach does not extend that far. Kuiper belt dynamics do not sculpt orbits in that zone. Something pushed these objects to where they are. The most widely discussed explanation is an as-yet undiscovered large planet in the outer solar system, what has been called Planet 9 or Planet X. In 2016, astronomers Konstantin Batygin and Michael Brown proposed that the clustering of orbital elements among extreme scattered disk objects and inner Oort Cloud candidates could be explained by a planet with perhaps 5 to 10 Earth masses orbiting somewhere between 300 and 800 AU on a highly eccentric orbit. If such a planet exists, it would have been scattered outward during the early solar system, and its gravity would be quietly shepherding the inner Oort Cloud population, explaining the clustering of orbits that has been observed. As of 2026, Planet 9 has not been found. Dedicated searches have not detected it, but they have not ruled it out either. The region of sky it would need to occupy is large, and a distant, cold, dark planet would be extremely difficult to detect. The Vera Rubin Observatory, the large survey telescope that began operations in the early 2020s, is among the instruments most likely to find such a world if it exists. Its wide-field surveys of the sky will detect large numbers of faint moving objects in the outer solar system, building up statistical samples large enough to test whether the orbital clustering is real or an artifact of observational bias. Whether or not Planet 9 exists, the orbital clustering of Sedna-like objects is a genuine puzzle, one that points toward processes in the formation and evolution of the inner Oort Cloud that we do not yet fully understand. The Oort Cloud, even now, is generating new questions at its innermost edge. There is also a broader pattern here worth noticing. Every time astronomers have looked carefully at the outer solar system, every time they have built better instruments, pushed to fainter magnitudes, surveyed larger areas of sky, they have found more. More Kuiper belt objects, more scattered disk objects, more complex orbital structures than any previous model predicted. The outer solar system has consistently surprised us. Each discovery has revealed new populations, new dynamical families, new evidence of processes that were either unknown or underestimated. There is no reason to think the Oort Cloud will be any different. When and if we develop the means to probe it more carefully, through space-based observatories, through more sensitive surveys, through dedicated outer solar system missions, it will almost certainly reveal structures and populations and histories that we have not yet imagined. The Oort Cloud is not a solved problem, with known properties awaiting confirmation. It is an open frontier. There is a connection between the Oort Cloud and one of the oldest questions in planetary science, the origin of water on Earth. Water is abundant in the outer solar system. The icy bodies of the Kuiper belt and Oort Cloud are, in large part, composed of water ice. But Earth formed in the inner solar system, inside the so-called snow line, the boundary within which water ice could not condense during the solar system's formation because temperatures were too high. Earth should have formed largely dry. And yet, Earth has enormous amounts of water. The oceans are deep. Water permeates the crust and mantle. Life, as far as we know, requires liquid water. And life exists here. Where did Earth's water come from? One long-standing hypothesis is that comets delivered a significant portion of it during the period astronomers call the Late Heavy Bombardment, roughly 3.8 to 4 billion years ago, when the inner solar system was pelted by debris, stirred up by the migration of the giant planets. Some of those impactors likely came from the outer solar system, from the population of objects that would eventually settle into the Oort Cloud. The evidence is more complicated than this simple picture suggests. The ratio of heavy water, in which one of the hydrogen atoms has been replaced by deuterium, to ordinary water, is a chemical signature that varies between different populations of solar system objects. In most measured Oort Cloud comets, this ratio is roughly twice the ratio found in Earth's oceans. That mismatch suggests that comets from the Oort Cloud were probably not the dominant source of Earth's water. Asteroids from the inner asteroid belt, which have a closer isotopic match, are now thought to have contributed more. But the story is not closed. Some comets, particularly those originating from the Jupiter family of short-period comets, which are thought to come from the Kuiper belt, have water with an isotopic ratio much closer to Earth's. The mix of sources, the relative contributions of comets, asteroids, and water-bearing hydrated minerals delivered during accretion remains an active area of research. What is certain is that the icy bodies of the outer solar system participated in the early bombardment of the inner planets. They left a fingerprint on the worlds we now inhabit. Some fraction of the water in every ocean on Earth, every drop of rain, every river, every cell, in every living thing, came from the outer solar system. Perhaps from the very region we are talking about tonight. It is a strange and humbling thought. The Oort Cloud is not merely an abstract astronomical structure sitting at an unreachable distance. Its material participated in the creation of the conditions for life. Its comets struck the early Earth and contributed something, perhaps the water, perhaps organic molecules to the chemistry that eventually became us. There is a connection, however indirect, between the cold, dark archive at the edge of the solar system and the warm, wet, inhabited world at its center. It is worth thinking for a moment about what it would be like to be out there. At 50,000 AU, roughly the middle of the Oort Cloud's outer region, the Sun is not a disk. It is not something you can point to and say, "That is our star." It is simply the brightest star in the sky. Brighter than anything else, certainly. But still, just a point of light. There is no day. There is no warmth. There is no solar wind of any significance. The solar wind loses coherence long before reaching these distances, fading into the broader interstellar medium. There is nothing. Blackness in every direction. The background stars almost identical to what you would see from anywhere in this region of the galaxy, and one slightly brighter point that is the Sun. If you were somehow standing on one of the icy bodies out there, a dark, porous, loosely bound aggregate of ice and dust, perhaps a few miles across, you would be moving so slowly, relative to the Sun, that you might not notice you were in orbit at all. The orbital velocity of an object in the outer Oort Cloud is vanishingly small. At 100,000 AU, the orbital velocity is roughly 100 meters per second. For reference, The speed of sound in air at sea level is about 340 meters per second. An Oort cloud object moves more slowly than sound travels through air. The orbital period at that distance is measured in millions of years. A full orbit around the Sun takes anywhere from 1 million to tens of millions of years. During the entirety of recorded human history, roughly 5,000 years, an object in the outer Oort cloud would have moved an imperceptibly small fraction of its total orbit. You would have to observe it for thousands of years to detect any motion at all. From your perspective on that ice and dust world, you would be effectively stationary. The stars around you would barely shift. The galaxy would look almost exactly as it does from Earth, because you are only 1.5 light years away from Earth. And the galaxy is 100,000 light years across. You would be in the most profound silence imaginable, wrapped in cold that has not changed in 4.5 billion years, surrounded by darkness, so total it would be difficult to describe to someone who had only ever known daylight, with a bright star somewhere in the sky that you would have to remind yourself is the sun. And in that silence, in that cold, you would have some faint chance of encountering another object. Not because the Oort cloud is dense, it is extraordinarily sparse, but because there are so many objects spread across such an enormous volume that some of them will, by chance, pass within detectable range over the course of billions of years. Even so, at typical Oort cloud densities, the average distance between neighboring objects is estimated at tens of millions of miles. The Oort cloud is almost impossibly empty. Billions of objects, and you could wander between them for years without encountering one. The Oort cloud does not just define where the solar system ends. It also defines something about what the solar system is. We tend to think of the solar system as a warm, busy place. Planets with weather and geology and, in at least one case, life. Moons with subsurface oceans. Rings sparkling in sunlight. The asteroid belt with its tumbling rocks. The solar system as a vibrant, active, populated neighborhood. And all of that is real. All of that exists. But when you account for volume, when you ask what fraction of the solar system's total volume is occupied by planets, moons, rings, and asteroids versus what fraction is the cold, dark, nearly empty volume of the Oort cloud, the result is humbling. The solar system is almost entirely the Oort cloud, and the Oort cloud is almost entirely empty. An extraordinary region of almost perfect nothing, scattered through with billions of frozen messengers from the beginning of time, held loosely by a star's fading gravitational grip, slowly dissolving into the galaxy over the course of billions of years. There is something almost philosophical about the Oort cloud's place in the solar system. It is simultaneously the solar system's largest structure and its most neglected. When people talk about the solar system, they talk about planets, moons, rings, asteroids. Sometimes they get as far as the Kuiper Belt and Pluto. Rarely do they mention the Oort cloud, the enormous dark halo that surrounds everything and constitutes the vast majority of the solar system's volume. And yet, the Oort cloud is, in a sense, more fundamental than most of what gets discussed. It is the closest thing to the original material of the solar system's formation that still survives in pristine condition. Its objects have sat in cold storage for 4.5 billion years. They are older in their chemical memory than anything on Earth's surface, older than any rock, older than any ocean, older than any continent. When a comet arrives from the Oort cloud, and we collect its light, analyze its spectrum, catalog its molecules, we are reading a document from the beginning, from the molecular cloud that collapsed to form the Sun and everything orbiting it. The Oort Cloud is the solar system's oldest artifact, and it is sitting there, right now, as it has been sitting there since before any planet had finished forming, wrapping the solar system in its silent, enormous embrace. Holding on. Barely. But holding on. There is one more thing worth considering before we come back to Earth. We have talked tonight about the Oort Cloud as a feature of our solar system. But our solar system is not unique. There are hundreds of billions of stars in the Milky Way, and the vast majority of them are thought to have formed in stellar clusters, the same kind of environment where Oort Cloud analogues would naturally develop. If the giant planet migration model is correct, and if giant planets are common and based on exoplanet surveys, they appear to be then Oort Cloud analogues should be common too. Most solar systems should have vast, dark halos of icy debris surrounding them, left over from their formation, slowly being depleted by galactic tides and stellar passages. Every star system within a few light years of us, Alpha Centauri, Barnard's star, Sirius, likely has its own equivalent of the Oort Cloud. And because those systems are themselves only a few light years away, and because their Oort clouds extend a light year or more from their central stars, the Oort clouds of neighboring stellar systems may actually overlap. The outer edges of the solar system's Oort cloud and the outer edges of the Alpha Centauri system's equivalent reservoir may interpenetrate, sharing space, allowing material to pass between the two systems. In this picture, the nearby stars are not isolated islands, separated by the void of interstellar space. They are surrounded by vast, overlapping halos of ancient debris. The gap between them is narrower than it appears. Not narrow, by human standards, still incomprehensibly vast by any familiar measure. But the solar system and its nearest neighbor may, in the most technical sense, share territory. The interstellar space between the stars is threaded with the outermost debris of the systems on either side. This image of stellar systems as vast, interpenetrating halos of ancient ice and rock, with dense planetary systems buried deep at their centers, is very different from the standard picture. It suggests that interstellar space is not quite as empty as it seems, that the boundaries between solar systems are not sharp, that the galaxy, at its finest scales, is filled with slow-moving debris from billions of planetary formations, drifting between the stars on journeys that last longer than any civilization has ever lasted. The Oort Cloud connects us to the galaxy. It is where our solar system ends and where the galaxy, in a sense, continues. There is a concept that helps clarify just how remarkable the Oort Cloud's existence is, and that concept is time. Not time in the abstract sense, but deep time, the unimaginable spans of years over which the Oort Cloud has existed, evolved, and persisted. The universe is approximately 13.8 billion years old. The solar system is approximately 4.5 billion years old. That means the Oort Cloud has existed for roughly 1/3 of the entire history of the universe. While stars were being born and perishing across the galaxy, while galaxies were colliding and merging, while the cosmic web of filaments and voids was slowly assembling itself, from the density fluctuations of the early universe, the Oort Cloud was here. Every comet that has ever fallen inward and been visible from a world in the inner solar system has done so against this backdrop of deep time. Every spectacular display in the sky has a common origin. The comets that ancient astronomers recorded with wonder and apprehension. The comets that medieval scholars interpreted as omens. The comets that modern scientists analyze with spectrographs and mass spectrometers. Every single one of them originated from a structure that has existed since before complex multicellular life appeared on Earth. The Oort Cloud was ancient when the first fish swam in Earth's oceans. It was ancient when the first land plants colonized the continents. It was ancient when the dinosaurs appeared, dominated, and were extinguished. It was ancient when our earliest hominin ancestors first looked up at the night sky and wondered about the lights they saw. And it will be ancient when whatever comes after us looks up at the same sky. This persistence, this implacable, cold endurance across geological and cosmological time is part of what makes the Oort Cloud such a philosophically interesting object. It has no memory. It has no awareness. It does not know it exists. But it has outlasted everything that has come and gone in the inner solar system. Continents have rifted apart and collided. Mountains have risen and been eroded to plains. Species have appeared and vanished. Mass extinctions have swept the biosphere clean and given rise to entirely new ecosystems. And throughout all of it, the Oort Cloud has sat there in the dark, barely changing. Its orbital periods are so long that the entire span of complex animal life on Earth represents less than 2 full orbits for even the innermost Oort Cloud objects. An object at 5,000 AU near the inner edge completes one orbit in roughly 350,000 years. All of recorded human civilization takes up only a tiny fraction of one orbit. The Oort Cloud operates on timescales that make human history feel instantaneous. It is useful to think carefully about why astronomers are so confident the Oort Cloud exists, given that no one has ever directly seen it. Science is often portrayed as a discipline of direct observation. You look at something, you measure it, you know it. But some of the most important discoveries in the history of science have been inferences rather than direct observations. Neptune was predicted before it was observed, because the perturbations of Uranus's orbit could not be explained without it. The electron was understood decades before it could be individually detected. Dark matter was inferred from galactic rotation curves, long before anyone found a viable candidate particle. The inference from cometary orbits to the Oort Cloud's existence is in this same tradition. It is not a guess. It is the result of rigorous mathematical analysis applied to a large body of observational data. The key facts that constrain the inference are: long-period comets arrive from random directions in the sky, not preferentially from the ecliptic plane. This indicates the source reservoir is spherical, not disk-like. The distribution of orbital energies shows a spike at aphelia of roughly 20,000 to 100,000 AU. This tells you where the reservoir sits. The flux of long-period comets has remained relatively steady over human observational history. Rather than showing a rapid decline, this indicates an ongoing supply mechanism, which is consistent with a large, slowly perturbed reservoir. The orbital parameters of the most extreme comets, those with the longest periods, the most randomly inclined orbits, the largest aphelia, are consistent with being recently injected from the outer Oort Cloud by a gravitational perturbation. When you put all of these constraints together in a self-consistent dynamical model, you get the Oort Cloud. The alternative, that there is no reservoir and that long-period comets are somehow produced by another mechanism, does not work. No other mechanism produces comets with the right distribution of orbital energies, the right spatial distribution of arrival directions, or the right steady flux. The Oort Cloud is not a speculation. It is a conclusion. A conclusion reached by the same kind of logical reasoning that predicted Neptune, inferred atoms, and discovered dark matter. The confidence astronomers place in its existence is well earned, even without direct observation. There have been moments in the history of comet science that shed especially bright light on the Oort Cloud and its nature. One of the most dramatic occurred in the early 1990s, when a comet named Shoemaker-Levy 9 was discovered in orbit around Jupiter. This was already unusual, a comet captured into orbit around a planet rather than following a normal solar orbit. But what happened next was unprecedented. Shoemaker-Levy 9 had been torn apart by Jupiter's tidal forces into a string of roughly 20 fragments. Each fragment a discrete piece of the original comet nucleus, all strung out along the comet's orbit like pearls on a string. In July of 1994, those fragments slammed into Jupiter's atmosphere one by one over the course of about 6 days. The impacts were visible even through amateur telescopes. They left dark scars in Jupiter's atmosphere, features larger than Earth that persisted for months. The event was a visceral, visible demonstration of what happens when an icy body from the outer solar system encounters a giant planet. Shoemaker-Levy 9 was almost certainly a Kuiper belt or scattered disk object rather than a true Oort Cloud comet. Its orbital history before capture suggested it had originated in the Jupiter family. But the basic physics on display was the same physics that applies to all cometary bodies: tidal disruption, fragmentation, high-velocity impact. The event made clear, in a way that no diagram or equation could, why impacts from outer solar system bodies matter. Jupiter took those hits. Its enormous gravity intercepted material that might otherwise have continued inward toward the terrestrial planets. Jupiter acts, in a sense, as a shield, capturing or deflecting a substantial fraction of the long-period comets that fall inward from the Oort Cloud before they can reach Earth. The degree to which Jupiter's shielding effect actually protects Earth is debated. Some models suggest that Jupiter deflects more comets toward Earth than it intercepts, depending on how you count. But the basic gravitational influence of the giant planets on the cometary flux is undeniable. The architecture of the solar system, the positions and masses of the giant planets, shapes which Oort Cloud objects reach the inner solar system, and how often. Every comet that has ever struck Earth, or been visible from Earth, has had its journey shaped by the gravitational gauntlet of Jupiter, Saturn, Uranus, and Neptune. Comet Hale-Bopp deserves more attention than it typically gets in discussions of the Oort Cloud. It was one of the most intensely studied comets in history, and it was bright enough to be visible to the naked eye for roughly 18 months, an extraordinary duration. Its perihelion, the closest approach to the Sun, was in April of 1997, and it was well observed by both professional and amateur astronomers around the world. Hale-Bopp is thought to have made at least one previous inner solar system passage. Its orbital period is estimated at somewhere between 2,000 and 4,000 years, meaning that, on a previous visit, roughly 4,000 years ago, it may have been visible in the ancient Middle East, possibly recorded by observers whose records have not survived or have not yet been fully interpreted. What made Hale-Bopp scientifically remarkable was the sheer richness of its chemical output. Astronomers identified more molecular species in Hale-Bopp's coma than in any comet previously studied. Among the compounds detected were complex organic molecules, ethane, acetylene, formaldehyde, hydrogen cyanide, and others. These are not exotic laboratory chemicals. They are the kinds of molecules that appear throughout interstellar space, in molecular clouds, in the regions where stars form. Their presence in Hale-Bopp's coma was further evidence of the deep connection between cometary material and the interstellar chemistry from which the solar system originally formed. The Oort Cloud objects are, in this sense, archives not just of the solar system's formation, but of the broader molecular inventory of the interstellar medium. The chemistry that formed in the molecular cloud before the Sun ignited the chemistry that pervades the space between stars, is preserved in the icy nuclei of Oort Cloud comets. When a long-period comet falls inward and sublimes, it releases that chemistry into the inner solar system. It is the interstellar medium announcing itself in the neighborhood of a star, carried by a messenger that has been in transit since before Earth existed. There is a category of science called astrobiology, the study of the origin, evolution, and distribution of life in the universe. It is a young field, partly because so much of its subject matter remains unknown. We know of only one example of life on Earth. We do not yet know whether life exists elsewhere in the solar system, whether it existed in the past, or whether the universe is teeming with life or largely barren. But the Oort Cloud is relevant to astrobiology in several ways that are worth examining. The first is the delivery of organic molecules. Long-period comets are known to carry complex organic compounds, the building blocks of biochemistry. Amino acids, the molecular components of proteins, have been detected in meteorites that are chemically similar to cometary material. Some researchers have proposed that the bombardment of the early Earth by outer solar system objects may have delivered a significant portion of the organic molecules that eventually participated in the brightenings. Origin of life. This is speculative, but not without supporting evidence. The late heavy bombardment period, when the inner solar system was under intense cometary and asteroidal assault, coincides roughly with the period when life is thought to have first appeared on Earth. Whether the connection is causal, whether organic molecules from the outer solar system helped catalyze life's origin, is one of the most debated questions in astrobiology. The second connection is more speculative, but more dramatic. Some researchers have proposed the idea of lithopanspermia, the hypothesis that life itself, not just organic molecules, can be transferred between planetary systems embedded in rocky material. An asteroid or comet large enough to generate impact ejecta moving at escape velocity could, in principle, launch fragments of the impacted world into space. Some fraction of those fragments, if they carried living organisms in a dormant state, might eventually reach another planetary system. The Oort Cloud would be a natural transit zone for such material. Objects leaving one star system's Oort Cloud and entering another's could carry embedded biological material across interstellar distances on timescales of millions of years. Whether any organism could survive the radiation environment and timescales of interstellar travel is deeply uncertain. The hypothesis of lithopanspermia is treated with skepticism by most astrobiologists. But it is not impossible, and the Oort Cloud is central to any version of the scenario. The third connection is more indirect. The impact record on Earth suggests that large cometary impacts have occurred multiple times in the past. The most famous example is the impact at the end of the Cretaceous period, 66 million years ago, that contributed to the extinction of the non-avian dinosaurs. The impactor in that event was most likely an asteroid, but the principle applies to long-period comets as well. Large impacts reset planetary environments. They destroy existing ecosystems, but they also open ecological space. The extinction of the dinosaurs created the ecological opportunity that allowed mammals, including the eventual lineage leading to humans, to diversify and expand. In this indirect sense, the delivery of impactors from the outer solar system, including the occasional long-period comet from the Oort Cloud, has been a shaping force in Earth's evolutionary history. The Oort Cloud has not been merely a passive archive. Through the comets it occasionally releases, it has reached into the inner solar system and influenced the history of life on Earth, indirectly, over immense timescales. But unmistakably, there are features of the Oort Cloud that even many astronomers do not think about often, because they are so far from the everyday concerns of observational astronomy. One of these is the question of what happens to Oort Cloud material in the very long-term future, not just over the remaining lifetime of the Sun, but on truly cosmological timescales. After the Sun becomes a white dwarf, the Oort Cloud will largely disperse, as described earlier. The objects released will drift into the interstellar medium. Over hundreds of millions of years, they will be accelerated and decelerated by the gravitational influences of other stars, molecular clouds, and the galactic potential. Some will end up captured by other stellar systems. Some will end up in the intergalactic medium, drifting between galaxies. Most will simply become part of the background population of free-floating, icy bodies in the Milky Way, one of a vast number of such objects produced by billions of planetary systems over the Bryce Galaxy's history. On even longer timescales, billions to trillions of years, in the future, the galaxy itself will change. Stars will continue to form and perish. The Milky Way will eventually merge with the Andromeda Galaxy and form a new elliptical galaxy. The populations of free-floating icy bodies, including the dispersed remnants of our Oort Cloud, will be scattered by the tidal forces of the merger, mixed with the equivalent populations from Andromeda's stellar systems. On timescales so long they are almost meaningless to discuss. The protons in the matter that currently makes up Oort Cloud objects may decay, converting matter to radiation. The universe may eventually reach a state of maximum entropy in which no structure remains. The Oort Cloud, like everything else, is temporary. It is just temporary on a grander scale than most things. 4.5 billion years of existence, with potentially several more billion years remaining before the Sun's death disperses it. This is a long lifetime, but it is finite. Everything the Sun has ever claimed as its own, including the most remote objects orbiting it in the cold dark of the Oort Cloud, will one day return to the galaxy from which the Sun itself originally formed. There is a poetic circularity to this. The material of the Oort Cloud was once part of a molecular cloud in the Milky Way. It condensed into a protoplanetary disk. It was shaped by the formation of planets and the migration of giant worlds. It was flung outward to the edge of the solar system, and eventually, over a timescale that dwarfs anything we can easily conceptualize, it will return to the galaxy. Dispersed, transformed, but carrying the isotopic and molecular signatures of its origin in this particular star system, in this particular part of the galaxy, at this particular point in cosmic time. The Oort Cloud is a temporary visitor, in the deepest possible sense. It is just visiting on a time scale that we can barely imagine. Tonight, we have covered enormous ground from the planets we know, through the Kuiper Belt and the scattered disk, out into the vast dark halo of the Oort Cloud, and beyond it, to the interstellar space where the sun's claim on matter finally ends. We have talked about the history of how this structure was discovered, or rather, how it was inferred from the orbital properties of long-period comets by one of the 20th century's most rigorous astronomical minds. We have talked about its structure, the inner Hills cloud, the outer spherical halo, the barely bound objects at its outermost edge, hovering at the boundary between the solar system and the galaxy. We have talked about the forces that shape it, the galactic tide, passing stars, the slow procession of orbital planes over millions of years, and the comets these forces release, sending them on multi-million-year journeys inward toward the sun. We have talked about what Oort Cloud objects are made of, ancient ices and organic molecules preserved in cold storage since the solar system formed, and what they tell us about the beginning. We have talked about the challenges of exploring it, the impossibility of sending any spacecraft there in any meaningful human timeframe, and what it means to know something profound exists that you can never directly touch. And we have sat with the scale, the true scale. The solar system does not end at Neptune. It does not end at Pluto or Sedna. It ends at 100,000 AU, 1.5 light-years out in a dark, ancient, slowly dissolving halo that most people have never heard of and that no probe has ever reached. Everything else, every planet we have visited, every moon we have photographed, every spacecraft we have launched, occupies a tiny fraction of the solar system's true volume. The Oort Cloud is where the solar system really ends. And it is far, far more than most of us ever imagined. There is a question embedded in all of this that does not have a clean scientific answer. Why should any of this matter? You cannot visit the Oort Cloud. You will never see an Oort Cloud object directly. The comets that fall inward from it are spectacular, but they are rare, and they disappear after a single pass. The Oort Cloud does not affect your daily life in any observable way. So why care? The answer, if there is one, lies in the value of knowing where you are. Human beings have spent most of their history not knowing where they were, not knowing how large the Earth was, not knowing how far away the moon sat, not knowing that the sun was a star, not knowing that the Milky Way was a galaxy, not knowing that there were other galaxies, not knowing that the universe had a beginning. Each time the picture expanded, each time the boundaries of the known were pushed outward, human beings were forced to update their understanding of their own place in things. And each expansion changed something. It changed what questions were worth asking. It changed what was possible to imagine. It changed, in subtle ways, how human beings understood themselves. The Oort Cloud is another expansion, another revision to the map. Before Oort's insight in 1950, the solar system ended at the planets, or perhaps at the asteroids, or at Pluto after its discovery in 1930. After Oort, the solar system became something fundamentally different. Vast, dark at its edges, connected to the galaxy through the tidal forces that slowly perturb its outermost objects, populated by billions of objects we cannot see. A structure extending not millions but trillions of miles from the sun. Knowing this does not make you safer or wealthier or healthier, but knowing it does something that matters. It locates you. It tells you that the star you orbit is surrounded by a halo of ancient material stretching 1/3 of the way to the nearest star. It tells you that the solar system you live in is not the compact, tidy arrangement of planets depicted in diagrams. It is something enormous and dark and full of history. And you, and everything you know, and everyone you have ever loved, exist in the innermost, warmest, most densely populated fraction of a percent of that enormous dark thing. The planets are the center of the solar system. But the Oort Cloud is the solar system. And somewhere, in that vast, cold, ancient archive, billions of frozen worlds are quietly orbiting a star that barely knows they are there, waiting, patient in the way that only things with no awareness of time can be patient, carrying, in their chemical interiors, the memory of a beginning that happened 4.5 billion years ago, and that we are only now learning how to read. The solar system is larger than it looks, and somewhere at its farthest edge, in the dark beyond dark, the last of our sun's domain stretches out toward the void, ancient, silent, and extraordinary. When Jan Oort published his paper in 1950, he was working with limited data. The number of comets with well-measured orbits was small by modern standards. The mathematical tools for modeling the dynamics of a vast reservoir of bodies were primitive compared to what is available today. Computers capable of running meaningful simulations of solar system dynamics were either in their infancy or non-existent. And yet, the logic of his argument was so clean, so well-founded in orbital mechanics, that it was immediately recognized as compelling. It did not take generations of further evidence for the astronomical community to accept the broad outlines of his proposal. The idea resonated because it was elegant. It connected the observed distribution of comet orbits, a pattern in the data that had been unexplained, to a physical reservoir whose properties could be predicted from first principles. It explained why long-period comets came from random directions. It explained why they had such enormous aphelion distances. It explained the observed flux, the rate at which they arrived in the inner solar system. And it did all of this with a single coherent picture. A vast, roughly spherical shell of icy bodies, formed from the debris of the outer solar system's formation, slowly perturbed by the galaxy. In science, when a single idea explains multiple independent observations simultaneously, that is a strong signal. It does not guarantee the idea is right. History contains examples of beautifully elegant theories that turned out to be wrong. But the coherence of the Oort Cloud model, the way it ties together orbital mechanics, solar system formation theory, and galactic dynamics into a single self-consistent picture, is one of the reasons it has remained not just accepted, but uncontested as a basic framework for nearly 75 years. The details have been revised. The quantitative properties of the cloud, its mass, its exact extent, the shape of its inner component, have been refined by subsequent work. The role of the galactic tide was not fully appreciated in Oort's original paper, and was developed significantly by later researchers. The Hills cloud was proposed as an extension and refinement. The connection to solar system formation models has been made more explicit by modern numerical simulations. But the core idea that a vast reservoir of cometary bodies surrounds the solar system at distances of thousands to hundreds of thousands of AU has stood the test of time, as well as almost any idea in the history of planetary science. It is worth paying attention to what the study of the Oort Cloud tells us about scientific methodology more broadly. Science progresses not only by direct observation, but by inference from evidence that exists within reach. Sometimes, the phenomenon you want to understand is not directly accessible. You cannot send a probe to a black hole. You cannot observe the interior of a distant star. You cannot watch a galaxy form in real time. You cannot reach the Oort Cloud. But in each of these cases, you can observe the signatures that the inaccessible phenomenon leaves in the data you can collect. The gravitational influence of the black hole on nearby matter, the pattern of light emitted by the stellar surface, which encodes information about the interior through the physics of stellar structure, the redshift and chemical composition of distant galaxies, which tells you about the physics of galaxy formation, the distribution of cometary orbits, which tells you about the reservoir that produced them. This is inference. It is not guessing. It is the disciplined application of known physics to available data to constrain the properties of things you cannot directly observe. It requires care, rigor, and a clear understanding of what assumptions go into the inference and how sensitive the conclusion is to those assumptions. Oort was explicit about the limitations of his inference. He acknowledged the small size of his comet sample. He acknowledged the uncertainties in the orbital calculations. He proposed the model not as a certain conclusion, but as the most natural interpretation of the data. That intellectual honesty, that clear-eyed acknowledgement of what is established and what is assumed, is part of what made the paper a model of scientific reasoning as well as a landmark. Result: the Oort Cloud is a reminder that some of the most important things in the universe are known not by looking directly at them, but by paying careful attention to the evidence they leave behind. The Milky Way is a spiral galaxy containing somewhere between 100 billion and 400 billion stars. Our Sun is one of them. Located roughly 26,000 light-years from the galactic center in a minor spiral arm called the Orion Spur. The Sun orbits the galactic center at roughly 500,000 miles per hour, a speed that sounds fast but still requires 225 to 250 million years to complete one full orbit. In the Sun's lifetime, it has completed approximately 20 of these galactic orbits. The Oort Cloud has accompanied the Sun on every one of these journeys. It has traveled with the solar system around the galaxy 20 times. It has passed through regions of higher and lower stellar density. It has crossed the galactic plane multiple times. It has been shaken by the tidal forces of the galaxy and nudged by the gravity of passing stars. Through all of this, it has persisted. Depleted, yes. Shaped and reshaped by the forces acting on it, but still there. Still surrounding the solar system in its enormous, dark halo. Still holding billions of objects in orbits so slow and so vast that the word orbit almost seems inadequate. Still sending the occasional comet inward, still releasing the occasional object to wander interstellar space, still balanced at the knife edge between the Sun's gravity and the galaxy's indifferent pull. When you think about the Oort Cloud in this context, not as a static snapshot, but as a 4.5 billion-year-old structure that has traveled around the galaxy 20 times, while being continuously eroded and perturb the scale of what we are discussing, becomes almost impossible to hold in the mind all at once. And yet, it is real. All of it is real. The mathematics describing it is well understood. The physics is not exotic. There is no mystery in the mechanisms involved, only in the details, in the quantities, in the precise properties of the reservoir we cannot directly observe. The Oort Cloud is perhaps the most mundane, extraordinary thing in the solar system. Mundane, because it is made of ordinary ice and rock, because it obeys ordinary gravitational physics, because it formed by ordinary processes of planetary formation and debris scattering. Extraordinary because of its scale, because of its age, because of its position at the very edge of everything the Sun has ever claimed, because of the way it connects the solar system to the galaxy and to the deep past of the universe. The Oort Cloud is where our solar system ends. And understanding that truly grasping it changes the picture, not just of the solar system, but of what it means to live inside one. We orbit a star. That star sits in a galaxy. And all around that star, surrounding it in every direction, extending for a distance measured in light years, is a halo of ancient frozen worlds. Too dark and too distant to see, too remote to reach, too slow to watch. They have been there since the beginning. They will be there for billions of years more. And every once in a long while, one of them is dislodged. It begins to fall. Slowly at first, then faster. The Sun's gravity, drawing it inward across distances that take millions of years to cross. The volatile ices on its surface remain frozen as it passes through the outer solar system, too cold to sublimate, too far from the Sun to feel its warmth. But, as it crosses Jupiter's orbit, something begins to change. The temperature creeps upward. The outermost layers of ice begin to sublime, going directly from solid to gas, releasing molecules that have been locked in that nucleus since before Earth existed. A coma begins to form. Gas and dust billow outward from the surface. The solar wind pushes the gas away from the Sun, forming the ion tail. Pressure from sunlight pushes the dust, forming a second tail. The comet brightens. And if the orbital geometry is right, if the comet passes close enough to the Sun at the right time of year, when it is visible from the right part of Earth, people look up. They see it. This object that has been traveling for millions of years. This messenger from the edge. This ancient, frozen archive of the solar system's beginning, now blazing for a few weeks or months as it rounds the Sun and begins its long fall back outward. The encounter with the Sun may have changed it, stripped away some of its most volatile outer layers, altered it chemically in ways that will persist. Or it may return to the Oort Cloud, settling back into a new orbit with a slightly shorter period, to fall inward again millions of years hence. Or it may be ejected entirely given a gravitational nudge by Jupiter that sends it onto a hyperbolic trajectory, escaping the solar system forever. Either way, its brief passage through the inner solar system is a moment of contact, a moment when the outermost and innermost parts of the solar system meet, when the ancient and cold and dark briefly touches the warm and bright and alive, when the edge communicates with the center. That communication has been happening for as long as the solar system has existed, and it will continue to happen in the silence and the dark, long after we are gone. The Oort Cloud sends its messengers. We receive them. And for a brief time, under a night sky lit by a blazing comet, we are connected to something that began before memory and will outlast everything we know. Good night. Sleep well under the stars. The edge is out there, in the dark, where the Sun lets go.